The next step for the next little while will be a hands-on section, and I'm not the best at these, so you will get confused, and that's my fault. I'm just telling you right now. What we've tried to do is put on these flash drives some Skyline files and some data, sort of like a bake show, to walk you through from, like, we're going to teach you how to do something, and then you begin with a blank Skyline slate, and then we'll take you through several steps in the process and show you what the final outcome should look like. So I will begin with the presentation, but then there will be times I'm going to stop and say, look for this file on your USB drive. Is everybody ready? Okay. The other thing is, if you are confused or you are stuck, raise your hand, and Lindsay and Brendan will come over and help you. Don't be shy, because getting confused is not going to help you at this course. Okay. Does anybody know why we want to refine transitions? The answers are right there. Right. So if we're taking data-dependent things into a targeted run, obviously we want to target the best transitions that are the most selective and will give us the best quality data. Refining is also a nice thing to do if you're working on high-res accurate mass platforms and doing PRM and collecting all the MS2, because you still have to process that data and know which transitions are the ones you want to use for quantification and reproducibility and all those things. So optimizing the transitions will overall give you better quality data. So everybody fire up Skyline and go to blank documents, and you should get a page that looks like this. Anyone having any problems with this part? That's good. Okay. So let's pretend we have discovery data. I have data files if you all want to practice. They are not on the USBs because we had problems with the file sizes and getting everything on there. But I have some on my hard drive if you want to practice. But this is the general process, how you would use raw files you generated on a data-dependent platform and searched with some search engine. And so in your Skyline file, go up to Settings on the top menu, and then Peptide Settings, and you should have this window pop up. Everyone give me like a nod or something when you got it. Good, okay. Then, under the Library tab, you want to go to Build. When you do that, this window should pop up. And this name was something that I came up with, but I would try naming it that, and then you should be able to go into your little thing, your flash drive, and find that file. So that'll be like, 2 minutes later, the thing coming out of the oven that's fully baked, but didn't really take that long. That'll be the end product.
Plasma FX.
Yes, Plasma FX. The FX is for fractionated. If you were to build this from scratch with these search data files, what you would do is you would put in your file name, tell it where to go. You would select an output path. And then for now, I keep everything as the default, just for ease of getting through this. Then, when you would go to next, it would say, all right, well, where are those search files that you need to put in? You don't have these raw search files on the flash drive, so we're going to just kind of cancel out of this, back out of this step. But if you added them and then hit OK, then the last step would be checking that box and making sure that box is checked, so that the spectral library will be visible in Skyline. Okay. All right, so did everybody find, let's go back. Did everybody find this Plasma FX library? It should have a BLIB file extension. Okay. So what we'll do here is, instead of replacing it, you should be able to like just check it. The main thing we want to do is get this library activated in Skyline.
Yeah, so when I go. Alright, we'll walk through how to just activate the library because it's present on those flash drives, unless you deleted them. There we go. Alright, so peptide settings. If everybody tries to back up a step and goes from, you see on the library window, oh boy. Cancel. So while you have this library thing open, go to edit list and then add, not build, because the library already exists, so we're going to add it. Whereas if you were to start from scratch, you would want to build one. And then here you should be able to point to this library on your flash drive. All right. And then under the data directory, do you see the NEU Skyline Plasma Fix blib? Does anybody not see this? We good? All right. So then you click that. I usually just name it the same name. Copy, paste. See if that works. All right, it's there. Did everybody get that far? Okay. We hit OK, and then you check it because you want to use it. So the settings that pop up are pick peptides matching library. So if you bring in peptide sequences or a FASTA file or a proteome, then it will match things that are in your spectral library. So that's why I have that. Rank peptides by picked intensity or spectrum count. This is something you can also play around with and see what works best for you. I'm just going to leave it blank for now. And then you could also limit the peptides per protein. Let's say you're doing a plasma analysis and you have 492 peptides from albumin and you don't want that many. You could limit it to like 5 or 10. Yes.
So the ranking is on the intensity or spectral count? Which is different?
Whatever you like. I don't think there's general consensus across all of mass spectrometry. I think some people do favor spectral count, or what you said. So I think it's just, my best answer to this is pick what you want to do and then generate enough information to be able to defend your choice, right? Because someone's always going to ask, and as long as you can defend it with, well, these are the 6 reasons why I chose that, and here are the 6 why I didn't choose that way, then it's hard to really dispute. And if someone does dispute it, then you learn something and maybe do something new. Okay. So now that, was there a question? No. Okay. Is everybody up to here so far? It doesn't look like we did much yet, but trust me, we will.
Okay, so now the next thing is we're going to import a FASTA file. So this is a human proteome database. So if you go to File, Import, whoops, FASTA, click. And do you see on that drive under Data, there's the Uniprot Human Proteome FASTA? Everyone see that? Click it. I double-clicked it. And now it's going to ask you, so, oh, it's importing. Oh, yes, question in the back?
So do we have to add any modifications?
Not at this point. That can be done at some point. So your searched files that are supporting the library that were used in this generation, they will have a modification associated with them. All right, and you'll have to forgive me. I've been using Skyline so long that it's been a really long time since I've started up the software fresh and had to tweak things like modifications. And so I usually always have a carboxyamidomethyl by default because I reduce and alkylate. Yes?
I have a question, Susan. What was the FASTA recording again?
Uniprot. It's right.
Human proteome.
It's the one that was right here. Hold on. Is it the same FASTA? This one?
Yep.
Okay. Good. Okay. So what Skyline did is it just brought in a whole bunch of proteins, and you can see how many proteins it brought in because it says 856. And then it tells you how many peptides it brought in, 2,768. And then right now, we have one precursor for peptide, and it's showing all of the transitions that are like preset in my Skyline document. Okay, and so I usually keep an eye on that corner section so I can see what's going on. If you expand that first protein, you'll notice that there are these little, so first of all, the squiggly ribbon is protein, like intact protein. And so that top one is the name of the protein with the accession number. If you just place your mouse over it, then it'll show you all the information. And then the blue peptides are the ones from that protein sequence that you have in Skyline. Then, if you look where my cursor is here, that little black spectrum looking icon means that there is an MS2 spectrum in the library with this.
Can I ask a quick question?
Yes.
How many people are actually working right on the flash drive? Most of them. Okay, so I guess after this current one, I don't generally encourage people to work directly off the flash drive. I usually try to have people copy the data off the flash drive onto your local drive. So we'll go ahead and keep going with this one, but yes, somebody has already run into a problem with the flash drive. So the next thing we do, let's try to get everything off to like your documents directory, some working directory. And the other nice thing about that is that if you mess something up, you still have a copy.
That's true. Okay, so if you click on that first peptide sequence, you may, the way mine showed up is it looked like this, where I had a gray box in the middle and then my spectrum's on the right. Is that how everybody's seeing it? Okay, so what I do is I just grab that plot up at the very top and I'll make it my main plot because right now we don't have any other data, so I want to see as much of this as I can. And then if you right click and check the B ions and the Y ions, oh, grab,
Well, I'm grabbing it, but now I'm
like that.
Yeah.
So you have to move it where one of these gray little boxes is, and then you'll see what it'll look like. If you put it on the edge, it'll look like that. If you put it on the top. So you have to anchor it to one of those. Yeah, it takes a little getting used to. That's for sure. So here, once you make sure your B ions and your Y ions are checked, check that your charges 1, 2, and 3. 3 may not be necessary, but definitely the 1 and 2 should be checked. And so this is showing which ions. So it's matching up from the MS data what ions are present and matching in your peptide. So if you expand that first peptide and you click on the product ions, it'll show you which of these is present in the spectrum. You see how it turns red? Y1, yeah. So there are ways to change the filtering of these product ions and peptides. The way we do this is settings, transition settings, and filter. Is everybody there so far? Okay. So if we decided, because we are just looking at spectral library data, and we want to start with a big wide funnel and then kind of take away things that aren't so useful instead of restricting it from the beginning. For precursor charges, I would put a 2, 3, which means the +2 and the +3 charge state. For ion charges, I would put 1, 2. Ion types, Y and Y right now is what I would recommend leaving it at. And this product ion selection window says that I would like everything greater than the mass to charge of the precursor on up, and here I will say through the last ion. It had been on 3 ions, which is why we only have 3 ions shown. But if we do that and click OK, then it's changing all of the transition settings somewhere. However, it doesn't really look like it actually changed these guys, because my mass to charge should be greater than the precursor. My Y1 isn't. So there's this little extra thing I sometimes do where I go into Edit, Refine, Advanced. Does everybody see that? Okay. And then I'll go Auto Select all, precursors and transitions. Once I do that, it should make more. There we go. It's still limited to 3 peptides right now. I don't know why that, or 3 product ions, sorry. Hey Brendan, do you have any idea why that is? In my transition settings, do I have a wrong setting where I want it to be product ion select?
Empty precursor the last ion? Like, oh, you want greater than empty precursor?
Yeah.
Okay, so go, so turn off the choline thing too. And then go to library. And then you have to
Oh, there it is, sorry.
All 3, but also unfiltered product ions. That one.
Okay,
Because otherwise it won't actually do empty precursor.
got you.
It'll ignore that.
Okay, oh, okay.
So this is like, oh, just do it from the types and ignore the filter.
Oh, gotcha.
And then this is use the filter.
Okay.
So, after doing this whole exercise, can they save the whole setting in one file?
Yep, once you save the Skyline file, these settings are saved with it.
So yeah, you can save, and you can even just save the settings. You go to settings, save current, and then you can give it a name, and then you can share it, and then settings share, and you make something for it.
Okay, so now you can see on our, we'll go back to that first one. Maybe not. Here now, this one peptide, it has a lot of product ions, but I asked it to give me 10. It's ranking them based on intensity. And so if I were to start up with a triple quad based method, I would start up with a list that has lots and lots of things, and then I would kind of get rid of anything that doesn't have good quality data associated with it. Okay. So let's go back to the thing. So then, now, here we go. Going back to the presentation, for peptide target selection, if you don't have data and you're not going from hypothesis-driven experiments, I would set up all peptides in Skyline. and then bring the FASTA file in just like we did. Even if you're coming with data sets and empirical data, you can do the same thing. You can bring those raw files in that you generated the spectral libraries with and see where these peptides are coming out chromatographically. And then from that process in Skyline, you can refine, optimize, and then refine again. So we kind of went through, whoa. All right, this was the example from earlier, that +2 and +3 charge state peptide, where the +3 had the higher intensity than the +2, but the +2 had good high mass to charge product ions. And so in a case like that, like I said earlier, sometimes it's better just to take those and generate the data on the instrument you're going to be performing the assay on. So the other thing, what is the dot product? This is something that's important when you're trying to match spectral library data with data you're acquiring on your instrument. All right, so this is that example from earlier where this one wins based on intensity, but this one wins on the number of product ions. If you summed all of these product ions, it may be around a similar intensity. And so I usually generate the data if I have time on the instrument and see which one looks better, see which one has fewer interferences, and so on. Okay, the dot product is, let's see if I don't have one in there. If you have a spectral library, the dot product can come in very handy when you're trying to figure out where in your data, where in your chromatography, the peptide that you're targeting comes out. Because unless you're super lucky, you'll have a lot of signal throughout the entire chromatogram, and it's not very straightforward all the time to figure out which is your peptide. Remember, peptides are made up of like 20 some odd amino acids in a certain combination, and all of these ones end in lysine or arginine, so you're going to have some overlapping signal. But this paper references the dot product, where it looks at the intensity and the mass to charge of your spectral library and compares it to your data, whether it's SRM or PRM or, yeah, I guess this is 2. And then it ranks how well those data match on a score of 0 to 1, with 1 being perfect. So we're going to go through some examples looking at the dot product to help us figure out which is the right peptide. So here's the peptide sequence. This is the full chromatogram. Which one, so Skyline picked this one. Which one would you pick? If Skyline didn't pick that, and these were your choices, how many people would go for the big one? I would probably go for the big one. I'd at least look at it, right? And then probably the 35, and then even the one at 45, I don't know if I would really look at it at all because it's so small. But if you zoom in on each of these, this is the one at 50.9. It really has only one transition with a tiny little one underneath it. That's likely not the peptide. If you look at the one at 35 minutes, which is this guy, second biggest, again, one transition with a whole bunch of little ones. This isn't usually how peptides look. But if you zoom in on the one at 45.2 minutes, you see a bunch of signal from all of your transitions. And the way that, I don't know, I think my mind just tunes to something after all these years, where when I see no straight across line, I'm like, oh, that has to be it. That has to be it. This doesn't happen with everything. So you really need to go in and look at the data. In this case, Skyline did a fair job picking it. But the other thing, aside from, let's go back for a second, this one, the dot products are shown. So here, the big one is 0.16. That's a terrible score. This one is 0.37. That's just slightly less terrible. And then this one was 0.92, which is much better to 1. And so looking at the dot product helps in this case. The other thing you can look at is retention time. So there's a hydrophobicity. This is one of the basic retention time hydrophobicity scores that you can look at in Skyline. There are other ones where you can do index retention time, which we'll get into later. But all of the peptides have a hydrophobicity based on their amino acid content. Not necessarily sequence, and it doesn't take into account post-translational modifications, but based on the amino acid content, there will be some kind of hydrophobicity score, and then Skyline will correlate the retention time of those peptides. And what we normally see is a decent regression with a little bit of drift around it, but what I found is using this this regression as a guide. This is that peptide at the 45 point whatever minutes. This is the one that's the right one. It's pretty close to the line. The others are earlier eluders and later eluders, and what that would do is that would make that spot move up or down off that line. This doesn't always work, but you can see the one at 50.9 minutes moved up there, and the peak at 31.5 minutes moved down there. So it's not helping the regression. Okay, so here's another example going through this peptide. Which one is the correct peak? So we've got dot products 0.73, 0.56, 0.6, 0.7, 0.7, 0.7, 0.6, 0.7. They're all not that good. Anyone have any ideas? I can't remember, so let's find out. As it turns out, it's this peak here, which your eye is not naturally drawn to, right? It's not really good looking. It's got a 0.73, but even though the dot product might not be that wonderful, it's kind of close to the regression, but the other options are much, much worse. Lower dot product and further away. So we kind of use it as a guide. Nothing, they're not all going to be perfect. They're going to be exceptions to this guide, which become frustrating and make you question, is that the right thing? But these are definitely good guides for us. All right, so this is another peptide. This has a dot product of 0.41. This one has 0.88, and this one 0.68. Anyone think this is the right one? How many think this one's the right one? I see some nods. This one? All right, so the one in the middle. I think that's what I would think too. If we look at, right, retention time. This one's interesting. It's got a terrible dot product, but it's right on the regression line. And this one has a much better dot product, but it doesn't exactly follow that hyperphobicity score. So there are going to be times when it doesn't match perfectly, but you do the best you can, and you just keep checking on your data. So what do you do if you don't have empirical data and dot product and spectral libraries? Which one is, so this is the peptide sequence. Anyone have any idea which one? This one's easy, right? You can see this one. Raise your hands. How many people think it's 33.7? No. 37.9. 43.6. 45.6. Okay. So everyone pretty much has a different opinion, right? So if I look at these and I compare where their retention time is, what's interesting is this one actually looks like this big purple one is more of an interference. You see how its apex doesn't line up and everything underneath it is a little off to the right? This is one that's tricky and you have to be careful of. This is not how normal peptides should look. Okay? This one has a lot of signal in it, but really none of the transitions have the same apex. Maybe the blue and the purple do, but nothing else really does. And this last one, even though it's not ideal, it's got, if you look at the very center, it's got probably the most overlap out of all the choices. But this was not an easy one to pick. This is like, you have to, and the retention time is not so close. So again, kind of another exception to the rule. And if you don't have spectral libraries, this is difficult. It's not a very straightforward and easy process for all of the peptides. And when you get those good ones, you're like, ah, thank God. And when you get ones like this, you go, well, I'll just collect as many product ions and precursor charge states as I can and make sure that it tracks through the data and then figure it out from there. Okay. Yes.
Are these data from triple point students?
Yes.
Is it possible that none of them are real?
Is it possible that none of them are real? I suppose, yeah, because this sample matrix is plasma, so it could be interferences, it could be another peptide, and it may not be the right thing, which is a perfect segue into how you confirm that, right? So that peptide was targeted in 2 different samples, a normal and a cancer, and what we found, it was a peptide that had other peptides from the same protein that were monitored at the same time.
And so if a protein is changing between two samples, the easiest thing to believe is that all of the peptides from that protein should have the same change. So if the protein is changing by 5-fold, the peptides should change by 5-fold. Of course, there are a lot of things that will affect that, but if you see that and all of the peptides from that protein have a similar response, change in response, then there's a good chance that it's the right peptide. It would be hard, the best way to confirm is by a standard, and then you know for sure, but often that can't be done right at the beginning. So what we saw was with that one particular peptide on the previous page, when I clicked through all the peptide selections options, this was the one that showed this difference between the normal sample and the cancer sample. And then we did replicates of normal, cancer, and so on. So it's clear there's a pattern here. And most of the other proteins and peptides we monitored in the sample, with the exception of a few, had no change. This was one that had change, and all of the other peptides from that protein showed this same one. And so that provides weight that it is probably the right peptide. Again, probably.
But more confidence.
Yes, more confidence, exactly. Okay, tips and tricks. When you have a lot of peptides present in your Skyline document, beware that there may be duplicate or repeated peptides, so make sure that the peptide in your document is unique. So if you have a Skyline file open, you can go to Edit, Refine, Remove Repeated Peptides. And then that'll get rid of the potential that you think you're monitoring for a peptide from one protein, but it's really present in other proteoforms, and it's not unique. Another thing to just always have in the back of your mind is this interference determination. So this was my first example when I was in grad school of this one peptide that I was looking at in 2 different cancer cell lines. One was regular, the other was drug resistant, and we were supposed to see a change in the intensity of this peptide. And I was monitoring 3 product ions, the Y4, 6, and 8, and this is from the heavy. And the response I was seeing didn't make a lot of sense between the cell lines and some other samples I was looking at. So I decided to look at the Y4, Y6, Y8 intensity. And you see how the Y8 is the tallest, Y4 is the second, and Y6 is the smallest. So when you are using the same model of instrument, whether in this lab or in a different lab, you should always get this pattern of both master chart spacing and intensity. So if you're using a Waters triple plot, it'll always give you the same pattern and intensity. If you're using a thermal one, it'll always give you the same pattern and intensity. So we can take this information and track it. So what I did is I normalized everything to the smallest ion so I could have positive numbers. And so if I take the peak area from the Y6 and divide it into the Y4 and the Y8, then I get this number, 3.85. My standard shows that same ratio, the heavy peptide. Now, that's just in solvent matrix. When I go into more complex samples, I see that, wow, these numbers are not matching the 2, and these numbers are not matching the 3. But my standard is coming pretty close to what is predicted. So when I went back over here, I noticed that my Y6 ion, when I actually looked at the data, was way more intense than the other 2. And so I knew the Y6 had an interference. And what that meant was I couldn't use the Y6 at all. And I had to figure out another ion to make sure that I could quantify appropriately without having something else mess up the quantitative accuracy. Now, that's a lot of math. Skyline has this great way now visually that will do this for you. So if you're monitoring 3 product ions, this is the heavy peptide and the contribution of signal from each of the 3 transitions. And this is over a response curve. So the heavy is spiked in a fixed amount, and the light peptides are increasing as you go left to right. So this heavy peptide transition, this is what you should see. It should be very reproducible and consistent. But the light, you don't see this same distribution until you're at the very high concentrations of the light. So what this means is when you're spiking in the light in various small concentrations, this purple product ion, the Y9, is too big. It doesn't match what the heavy response is, and we consider that an interference.
So visually, this is a really nice way to look at the data without having to do math, because that doesn't look like that, so something must be wrong. Any questions so far? All right. Other ways you can look at your data, particularly for interferences or if something's wrong with your instrument, is to look at the data in plot format. So Skyline can do this, and there's an external tool called Quasar, which can also do this. And it'll plot each transition as a different color. And this is shown on the log scale. I don't personally do regressions to determine the slope on a log scale. I do it on a linear scale. But for visualization, looking at it on a log scale is nice because the lower concentrations don't get bunched up. You don't have to expand and expand to see those. So on a log scale, ideally we'd expect to have a very straight response as the concentration decreases. But here, this one transition kind of peels away, and that's indicative of an interference in that one transition. If it was, and then we see the same thing over here, where a blue transition peels away and it doesn't follow the response of the other two transitions, which means it's an interference. Does anyone have an idea what this indicates? Does anyone know what I mean by endogenous?
There's a fair amount that's present in the sample. You weren't expecting something that didn't already exist in the matrix.
Exactly. Sometimes it's really hard to find your sample matrix that doesn't have your compound in it. In the case of CRP, it's pretty detectable in plasma even at low abundances. And so when you see all three of the transitions agree with one another, but not adhere to the line, particularly at the low end, that's indicating you're picking up endogenous levels of that protein in the sample. This one is just a hot mess because none of the, there's like a very terrible linearity to this, but the scatter is crazy. What happened here is that the electrospray from the nanotip was unstable. And so we were only getting about 4 points across the chromatographic peak, and the signal was very jittery. And so this is, a physical condition that leads to a math-based issue, which is calculating reproducible peak areas. This one is not detected because there are no points on this curve. This was an interesting one where when we spiked the peptide into the sample, we would get a very nice linear response, but when we spiked the protein into the sample, this peptide is an N-terminal peptide, and sometimes there are these exoproteases that go and just like gobble your peptides from one end to the other, and or your proteins, and that peptide was just never recovered. In the last one, does anyone know what's happening here? Those two transitions? So that is detector saturation. The reason that it's obvious to me is because I know more about this plot than you. The red, these are color-coded. The red transition is the most intense transition, followed by the blue, followed by the green. So because the green is the weakest, it's likely not going to have detector saturation, meaning so much of that transition is getting to the detector that the detector can no longer keep up. And so saturation is defined by this flatlining at the top, which we observe with the two more intense transitions and not the least one.
You have a really large working range, and you have to get up to this kind of concentration so that it provides or inform your decision to select for that weaker transition monitoring.
Yes. Yep, that would be something. So the question was, if you have to get up to ranges that high, would this kind of data influence choosing the most intense transitions or not? And of course, other ways around it are diluting the sample, so you can get to those higher amounts, and then you just have to do more math to factor in all the dilution steps you did. Yes, it just gets more complicated. So this is an external tool that we're not going to go over in great detail here. There's a tutorial that is much more thorough. This tool is called Quasar, where it takes your data and it carries it through a smaller bit of software called Audit, which looks for interferences and if your data are not reproducible. So you have to have replicates for this to work, and you have to have internal standards for this to work. Otherwise, you can skip that. The other component it does is it calculates limit of detection and limit of quantitation, and then it generates plots for you. This one for visualization, this one for calculating the response linear regression. And here, if there are any of these little tick marks at the bottom, they're color-coded based on which transition is affected. And this will tell you, like, there's something up with that most intense transition at this concentration. And then you can go in and look at the data and fine-tune where you're looking instead of spending all your time looking at everything. So, auto interferences are, they're a real thing, but I don't think they have a real name yet. We encountered these when we were looking at peptides and spiking them in light and heavy in differing amounts, and realizing that some of the Y ions from a peptide have a B ion that's the same exact mass. And so on a triple quad, they're impossible to resolve, and based on, this labeling might be a little off, but here, this Y6 and B7 ion are pretty much the same mass to charge, and so here are the exact masses. If you take the exact mass and divide it by their delta mass, if you multiply by 1,000,000, you need over 600,000 resolving power in order to make these two peaks in the product ion spectrum on a high-res accurate mass platform, and no one really runs that routinely because it takes forever, and you're not going to have like a lot of data points across your peak. So the best thing to do would be to just not use this one. This is probably why it's so tall, because some of it's from the Y6 and some of it's from the B7 ion. And so this is the kind of thing that it sneaks up on you. You don't realize that that's what's happening, but there are experiments you can do to check for it. So if you're using light and heavy pairs, it'll only affect one of those peptides, because the other peptide will either be labeled or unlabeled, and those product ions won't have the same exact mass. You may not want to just throw away that peptide, that product ion, if you don't see a B ion from it. Like if empirically, when you fragment it, that product ion is really only produced from the Y ion and not the B, then there may be no need to throw out that transition. So there are things you can do to evaluate this. And this is one example where we have Y and B ions that have large contributions, and some of them are overlapping. So we designed an experiment to measure what the actual contribution from each of these overlapping ions was. So first we would look at light and heavy and no matrix to see if there are any interferences, because then the interferences would be coming from themselves and not the sample matrix. And then increase the number of transitions to at least 4, because if one of the product ions is being interfered with by another one in that peptide, we'll have to get rid of it. And then combine the light and heavy synthetic peptides into 3 ratios. And we can calculate mathematically what the peak area ratio should be. It should be 0.005, 1, and 20 if we do light divided by heavy. So if we look at the data, these are 2 product ions that have potential for B product ion overlaps. And so we would expect here the ratio to be 1, here 0.05, and here 20, based on the way we combine our samples. And we could see that the Y10 and the Y11 are consistently no interference to all of these. So those are good to keep. And then we can calculate, based on the light to heavy peak area ratio, what the percentage of interference is. And so ideally you don't want any interference, right? But if you're stretched with some peptides that may not have a lot of product ions, at least you can gauge how much interference and what the percentage would be based on how much of the light is present in the sample. So again, this just helps to characterize your standards and your samples in matrices.
So I think there's only a problem when you use your internal standard actually as a standard, right?
It could be, or
If you have a candidate curve, it does qualify standard, then you have a problem with it.
but what if you have another one of your peptides interfering with another target? Like this is for auto interference, true, but there could be other things that could cause similar issues and similar interference responses. And so in general practice, it's not a bad idea to set this up. And often this can be sort of kill 2 birds with 1 stone, where if you're not sure how much of your standard to spike, that can be the one thing that is varied between these ratios. see like, oh, should I spike 5 femtomol or 50 femtomol or 500 attomol, and then adjust the light accordingly. So you can gauge what the best spike level is for your samples, and then assess for interference too. It's not wasted, particularly if you find that there are no interferences. It may be a bummer because you're like, oh, well, all that for nothing, but it's good because you've established you have no interferences. Duplicate ions, this will also take care of that kind of overlap issue in Skyline. So we start with this mass spectrum up here and from the spectral library, and then we click, right-click, check duplicate ions. It'll remove that Y6 that has a duplicate ion from its MS2, from the B. Okay. Whoops. Collision energy optimization is one of those things that will help you in the long run, but it's not always necessary. If you need that little 2-fold boost in intensity or little bit, and you have to have it, you can always do collision energy optimization. If you're detecting everything at a pretty good LOD, LOQ, then it's not necessary, and you could probably save time by avoiding it. But the main point to remember on a triple quad is that all of your ions go into Q1, and one at a time, precursors, one at a time, are selected and put into Q2 for fragmentation. All of those product ions leave, but the only one that gets out to the detector is the product ion that's selected. This happens sequentially. So if you're monitoring 5 product ions for a peptide, this happens 5 times for that peptide before it moves on to the next one. On high-res accurate mass, it's one thing is isolated in a quad, it's fragmented, and all of these are collected. Does anyone know why the triple quad doesn't do product ion scans? Super slow. Yeah, it takes like a second to do a range of 1,000 mass to charge. So if you're doing 300 to 1,300, every product ion scan would be a second. And they're just not designed for that, but they are designed for very precisely transmitting Q1 and Q3, which the quadrupoles on the high-res accurate mass are not. They cannot go down to that fine transmission bandwidth, whereas on the triple quads they can. Just little fun facts. So when you do collision energy optimization, again, because you separate and you detect these product ions individually, you can optimize for them individually, and they may not all have the same collision energy. And so what we do conventionally and historically, but hopefully not so much anymore, is we infuse a peptide with a syringe pump and ramp through the collision energy values and plot the product ions based on their intensity. And at some voltage, you'll have an apex intensity, and that will be the optimized collision energy for that product ion. Then, what Skyline does now is it allows us to plot the optimized collision energy based on the mass to charge of that peptide's precursor and generate a regression. This works very well, and it's got 2 different, or the potential to plot each plot based on a peptide's charge state, not just mass to charge. So your +2s will have one regression, your +3s will have another. If you have +4s, there could be another. And so here we've got an example of how the information is saved. This is an example for thermoquantiva. We've got the charge state, the slope, and the intercept for the +2 and for the +3. And these numbers change a little bit, but you're able to generate these data online using methods that Skyline sets out for you. And then when you bring the data back in, it will plot the data and generate these regression values, which is handy because the more data you have, the better those regression lines are. Okay. So the way that you can walk through importing results for this collision energy optimization is you would go to File and Import Results, but you would pick this Add One New Replicate, and you would name it. I usually name it something like CE opt, and this new replicate may actually be a series of several data files. And that's because you may have to run several data files to cover all of the peptides, all of the transitions, and all the collision energies. And so here I've got a series of 20 different runs where I'm bringing them all in, and I'm telling Skyline I'm optimizing collision energy in these raw files. When you do that, the data come in, and it matches up to all the peptides. And right now, it's showing all of the transitions for one peptide. And the thing that you need to change in order to see the effect of collision energy is you would right-click on this plot, click transitions, and single. If you do that, it'll change to this. And now I'm sitting up here, I have my precursor highlighted. So this is showing the signal summed from all the transitions at the precursor level for each different collision energy step. And these data are plotted over here, showing based on the different collision energy steps, where the red one was derived from that regression equation, that's your starting point. And then these are steps up, adding more voltage, down, decreasing the voltage. And it picks the apex and helps plot everything into, and retain all the information in the software. Okay, so it's important if you're doing this process to just fix your outliers, because if you have peptides that are out here and Skyline didn't pick the right ones or not the one you would pick, or even these outliers, then that takes those into account, particularly if you have a bunch down on one side or ones that weren't picked by Skyline. You'll want to fix those ahead of time, because that'll change the regression of the slope of the regression. So you see the difference? Okay. Then you can down view results. So this allows the data that you generated from the optimization, it allows it to be plotted and new regressions applied, so that the next time you go to do a run, you can say use optimized collision energies. When you do that, oh yeah, it's definitely important that this will throw off the regression. It doesn't have as large an impact on the +2s because the collision energy here, really collision energies barely even go out to that first decimal place, so this is really 19. However, with the +3, that's a significant difference before and after it was corrected. The 3 volts can cause a change in sensitivity. So it's important to make sure that you don't have any of these little outliers. That is an example of a peptide that just, there was no peak picked. Okay. Also, the +3 precursors that have +2 product ions. This is a weird phenomenon that I've seen on every triple quad, where the collision energy required to generate the product ions, if this is the predicted value based on the mass charge and charge of the precursor, +2 products need far less energy than is predicted than the +1 product ions for those precursors. And I've seen this on a bunch of instruments, so it's got to be some kind of ion physics thing. This is on a different instrument, same peptide. It's just highlighting the +2 product ion and showing that this is the one that without empirical data, Skyline would have said that one's good, but it will end up being something that's many volts less and increases the signal by like 3-fold. So that's impactful. Okay. You can also look at the data at the precursor level. As I mentioned, if you click on the precursor mass charge or the peptide, you'll see all of the sum signal at each collision energy value for all of the product ions. And if that's what you want, then the method can apply one collision energy value for all your product ions. Or if you want to fine tune it, you could do it at the product ion level, where now if you click on each of these product ions, it may have a different collision energy apex, and those different voltages would be applied on a product ion level basis, which would boost your sensitivity a bit. In some cases, a lot. So the question is, what does collision energy optimization buy you? If Skyline has an instrument type with a collision energy regression defined, you're probably already at a good starting point. You could ask your vendor what they recommend for these collision energy regressions. But the point is, this is before collision energy optimization. If you're starting with a good prediction, then optimizing doesn't really buy you a whole ton in many cases. It can, if you have the time and data time, instrument time, sample, it may be worth doing. But these are cases where you don't really get much of an increase, maybe 10%. This is the only one that has that double charge product ion where you get a serious boost. So it's one of those things That's entirely up to you. That's another doubly charged product ion. All right. Any questions so far? Okay. All right. So post-translational modifications are something that are often lost when you do fragmentation. I mentioned this earlier. If they are of important aspect to you, whether that they're present or their particular location in the sequence, then the triple quad may not be the best instrument for you. Especially not unless you have an exact internal standard. They do make phosphopeptides that are synthetic, or I'm sure you could get glycosylated ones, but you would want to make sure that everything co-elutes properly, because if you do the fragmentation, that side group may pop off and you won't be able to tell exactly where it is. So without an exact replicate heavy labeled internal standard, it will be difficult to know for sure what you're monitoring. Alternately, if you use instruments that can do electron capture dissociation or electron transfer dissociation, that process is gentler and that modification is usually retained, and so you can say that it's there and where it is in the sequence, which would push you away from triple quads. All right. Yeah, so transition selection and optimization are important because you want to make sure you're monitoring what you think you're monitoring. There are a lot of things you can do to improve sensitivity, but you have to approach it from a practical standpoint of how much time you want to invest in that, and is it worth the gain in sensitivity. If you're going to spend 3 months trying to optimize and make something more sensitive and it doesn't work, how much did you really want to gain, and was it worth kind of that waste of time? Always worry about interferences, from the sample itself in a solvent matrix to looking at different biological samples, looking at different donor samples. It's really important, because if you have an interference and are unaware, then you're misinforming, the data are misinforming, and it's not quantitative or accurate. And there's nothing wrong with manually looking at your data. However, you can go down a rabbit hole, so make sure you know when to stop and trust the software. And in that respect, Brendan had made leaps and bounds progress when we first started, because I was looking at tables of numbers to see if there were interferences, and I was going cross-eyed by the end of the night. And simple requests of, hey, I think it would be easier if this could be a visual approach, or something could look like this. And if you get enough people to agree with you and then ask for it as a feature, it could happen in Skyline. That's one of the nice things about it. Okay, any other questions?